Okay. So first of all, since I've been warned that we may possibly have there is a possibility that campus could be closed on Monday because of possible weather. I'm not saying it will be, but due to the possibility of it, I'm canceling the in-class quiz so we can have more time just to go through material. That's the reason I'm canceling it. However, at the suggestion of Jenna, you can all send her thank you emails. That in-class quiz I'm going to now convert to 10 bonus points for the exam, but you need to turn it in when you take the exam. All right, so it's your choice as to whether you want to do that or not. I will tell you there's some good problems on there as far as helping to prepare for the exam. We'll say that. Then the test is a week from today on Chapter 14. The next homework assignment, Homework 6, is due at that time. The take-home quiz that you should all have is not due at the test. I have extended that due date. For you guys at Eureka and Lafayette, because of your break times that differ from our break, because we have break a week after next. So your take-home quiz will be due by Thursday, March the 13th, because you guys don't have school on March the 14th. So turn that into your faculty people. And last of all, you should have review questions. Those should be available to you to help prepare for the test. And I will be posting the solutions to those this Sunday on Blackboard. Okay? All right. Anyway, so what we're on here is we're on section 14.7, and where we're looking at maximum and minimum values. And the first part of this that we looked at last time, we're finding local maximums and local minimums, and we use the formula D equals fxx times fyy minus fxy squared, and we apply this to critical points. And now what are we talking about for critical points for a function of two variables? Critical points are where both fx equals 0 and fy is equal to 0. So chances are we'll have more than one critical point for a function, and we calculate the second derivatives and plug in our x and y values for the critical points, and we'll get a number for this D. And then we have several cases. If D is a positive number, then we check fxx, and if fxx is positive, bigger than 0, we have what I call the smiley face situation, and we have a local min. That's one case. If D is positive, and then again we check fxx. Uh-oh, what's going on? Isn't it? It shows that I'm sharing the screen, but you're not seeing it? Okay, all right, good. Because I didn't want to repeat that debacle so quickly after the last time. Give me another month, and then let me repeat that. And then again, we check fxx, and if fxx this time is negative, then we have what I call the unhappy face scenario, and this means we have a local minimum at that critical point. Oh, I'm sorry. Yikes. Local max. Thank you, Nikesha. And then if D is less than 0, we stop right there for that particular critical point, because that's a saddle point. And then the last thing is if D would be exactly equal to 0, this test yields no information. And we went through a couple of examples applying this. This is called the second derivative test. All right. Okay. Now what we're going to do today then is look at a function of two variables over a enclosed set of xy values and see where it has the biggest value and the smallest value. Okay. So here we're going to look at fxy again on what's called a closed bounded set that we'll call, say, D. And we're going to see, let's put it this way, we're going to find its largest value over that set, and we're going to find its smallest value. Over that set. The largest value is called the absolute maximum. Absolute max. The smallest value is called the absolute min. Now, similar to functions of one variable, we know that we're only going to find the biggest and smallest values on just some of the points on our set D. So these are going to be located either at a critical point or critical points inside the set D. We could find them there, or on the boundary of D. All right. So, and this is actually a very abbreviated version of what's called the extreme value theorem. Okay. All right, so what I want to do, I'm only going to do one example of this. These problems can tend to be a little bit lengthy. You do have one on your homework. Well, you know, you can draw your own conclusions about the test, all right? Had me enough, you might know the answer, okay? That doesn't mean we don't need to pay attention, though, to this particular example. So here's our example. Find the absolute max and min values of, and here's our function of x and y, x squared plus y squared minus 2x over the closed triangular region with the vertices, okay, one of the vertices is 2, 0, the other one is 0, 2, and the third vertex is 0, negative 2. And last time I think it was the last thing we had looked at, as I drew a picture of this triangular area. So let's put that up here again. So let's put in here our y and x axes. Okay, one vertex is 2, 0, so 1, 2, 0. And the other two, 0, 2, 1, 2, and 0, minus 2. So those are the three vertices of our triangle, and so let's draw the sides that connect them. And what we have, of course, are three lines. This is our boundary, and I'm going to call this lower line, line 1, L1, the second one, L2, and the vertical one I'm going to call L3. Now, the first thing that we can do here with this problem is we want to get the critical point, all right, and see if we have a critical point that's on the inside of that triangle, all right? So let's find the critical point. So that means we need to do fx equal to 0 and fy equal to 0 for that. So let's see, here's our function, x squared plus y squared minus 2x. So fx is going to be what, 2x minus 2, and we set that equal to 0. That's going to be easy. And the same thing for fy, that's going to be, both the x's are treated as constants here, so that's just going to be fy is 2y, and we set that equal to 0. All right. So we only are going to get a single critical point here. We're going to have x, when we solve this, we get x equals 1, and of course y is equal to 0. So that's our only critical point. So if we plot this up here, that's going to be this point right there, 1, 0. So that's our sole critical point. All right. Now, one thing we're going to end up doing at the very end of this problem is comparing all various values of our function to see which basically is the biggest value, which is the smallest value. So one thing we need to do, we might as well do it right now, is plug this critical point into our original function to get a value, okay? Because the whole goal is to find the biggest value and the smallest. So let's plug into our function f. So that gives us what? So f of 1, 0 is 1 squared plus 0 squared minus 2 times 1, and that gives us a value of negative 1. Okay, so we want to somehow, we're going to look at that again when we compare, all right? Now comes the trickier part. Now we have to look at all three boundary lines here and obtain what this function, what kind of values this function has on the three boundary lines. All right. So the first thing I want to do here is to get equations for these three boundary lines. Notice they're all straight lines, so we can just use our y equals mx plus b formula to get the equations of these boundary lines. Now this line L1, it goes up 2 and over 2, so it has a slope of 1. M is equal to 1. And we know, well, we have 2 points that are on the line. So basically, well, also, not only that, but we actually know right here what its y-intercept is. The y-intercept is negative 2. So we can do directly y equals mx plus b. So this one is y equals 1 times x, or x, and our intercept is minus 2. So it's y equals x minus 2. I guess while we're at it, let's do the other two and then go back to the first line. So this second L2, now this one has a slope of negative 1. it goes up 2, but it goes down by 2 for the x value. So this one has m equals -1. And again, we have a y-intercept equal to 2. So we can get its equation, and this is going to be y equals minus x plus 2 for that particular line. And then finally, L3, well, that's a vertical line, and it's on the y-axis. So its equation is going to be x equal to 0. All right? Okay. All right. Now let's start with L1 here. What we need to find out here is where do we have a biggest and the smallest value on L1? Where do we have a biggest and smallest value on L1? Okay, now with L1, we found out that y is equal to x minus 2. So what I want to do is I want to take that substitution of x minus 2, put it into my original function for the y variable. So we notice that our original function is x squared plus y squared minus 2x. So I'm going to plug in x minus 2. So I have strictly one variable to work with. So that gives us x squared plus, now in parentheses, x minus 2 squared minus 2x. And then let's FOIL that out and combine terms, x squared plus x squared minus 4x plus 4 minus 2x, all right, and then combine like terms, and I get 2x squared, let's see, minus 6x plus 4. Okay. All right, so everything along that line, this is our corresponding y value, all right? Now, x here goes from what, on this line L1, our x values go from what to what? From 0 to 2. So this is for x less than or equal to 2, bigger than or equal to 0. All right. Now, actually, what this does now is this now reverts to the type of thing you would have had in Calc 1. Now you have a single variable function, and you have an interval of x values on which we're looking at. Okay? So where are we going to look to see where between x equals 0 and 2, how are we going to find, well, where's the biggest value of our function? Where's the smallest value? Well, we're going to look at the endpoint. That is absolutely right, one thing. But there's also something else we need to look at. Not necessarily. They don't just look at one. But where else can we have maximum and minimum values? There's a term for it. Critical points, right. So we also have to look for any critical points where x goes from 0 to 2. So we know for single variable functions, that's just, we look at the first derivative and we set it equal to 0. Okay? All right, so let's get the critical, and there's only going to be one critical point. I'm just going to get critical point. We're going to solve y prime equal to 0. Okay. Okay, well, what's the derivative of this? That's going to be 2 times 2, 4x, minus 6x, minus 6, equal to 0. And so that's a simple one. We get x is equal to 6/4 or 3/2. All right. So when x is equal to 3/2, we have a critical point. So one thing I want to do then is I want to plug in 3/2 into our function of a single variable because we have to compare values. So let's find out what the value is at that point. So let's plug in to 2x squared minus 6x plus 4. All right, so we have fractions, so we're going to have to do common denominators and all that good stuff. But I think we'll muddle through this, okay? So 3/2 squared is 9/4 minus 6 times 3/2 plus 4. All right, and let's see. Actually, right here, 2 into 4 goes twice. So I have 9/2 minus 6 3s are 18/2, and then 4 is 8/2. So I'll get, let's see what we get here. All over 2, 9 and 8 is what, 17, and 17 minus 18 is minus 1. So therefore our value here is minus 1/2. And we want to keep that handy also. All right. Now, as Cassandra said, we need to also check the two endpoints. So we need to plug 0 and plug 2 into our function. So let's check the endpoints. So let's look at x equals 0. Well, let's see. That's going to be 0, 0. That's going to give us a value of 4. All right? So that's considerably bigger than the values we've gotten so far. Now let's also look at the other endpoint, 2. Plug that into 2x squared minus 6x plus 4. So that's going to be 2 times 2 squared minus 6 times 2 plus 4. I think we're going to get 6 when we do this, right? Let's see. This is going to be 8. 4 is 12. Oh, we're going to get 0. We're going to, wait a minute. 0, right? You got 2? Because this is 2 to 8 plus 4 is 12. 12 minus 12 is 0. Okay, so our value is 0. All right. So we just want to maybe circle or put boxes around all these various values, because at the very end of the problem, what we do is compare all these various values. Okay, we're finished with L1. Now we have to do the problem's long. Now we have to do the same kind of thing with L2. All right? So you can see on an in-class exam, these could be lengthy problems. So I think I should put one in. Maybe as a bonus. All right, let's now look at L2. So what did we, let's go back, wait a minute. L2 was y equals minus x plus 2. And we plug that into our function, which is, our original function is x squared plus y squared minus 2x. All right. Okay. So now we do this, so therefore this, we have x squared plus minus x plus 2 squared minus 2x. Boil all this out, we get x squared plus x squared minus 4x plus 4 minus 2x. Be careful with minuses. And combining like terms, we get 2x squared minus 6x plus 4. Oh, wait a minute. That's sounding awfully familiar, isn't it? Notice what we ended up for L1. We had gotten y equals 2x squared minus 6x plus 4. So therefore, gods are being good to us here in this problem. I don't have to redo all the stuff that I did with the first one. We have the same values of x from 0 to 2. So I'm just going to have the same results as with L1. So that's what I'm just going to put here. Same results as with L1. All right, so that was quick. All right, it's looking better for a test now. And now let's look at L3, our last line. Now L3, that was, where's my picture of L3? There. L3, that was the line x equals 0. Now, if that was between, however, not the entire thing, that's for y going from -2 to +2, all right? So let's put this down. So it's x equals 0, but y is only going from -2 to a +2. That's our L3. All right. So let's then plug in 0 for x into our original function, which is x squared plus y squared minus 2x, and we'll get a new function. That'll be 0, that'll be 0, so all we get then is y squared. And then this is for -2 less than or equal to y less than or equal to 2. Okay, now with this one, all right, now we certainly can do the whole formal thing of getting the critical point. What would be the derivative here for the critical point? 2y, right? So our f prime is 2y. We set it equal to 0, and that only occurs when y is equal to 0. And then we check the two endpoints, -2 and +2, and we get, of course, the same values for either of the two endpoints. Okay, so these are the three values then that we obtain for the third line. Okay. So the final step in all this is just to compare the various values that we found and find out which one is the biggest value and which one is the smallest. That's all we do. So this is the last step, compare. So let's see here. Let me go back. What do we have here for? First of all, we had a critical point. And that was 1, 0. And the value that and so this is the point. The value that we got when we plugged that in was -1. All right. Then on L1 and L2, remember we got the same results for either one of those. We found that when x is equal to 3/2, the value that we get was -1/2. And then at the endpoints, x is equal to 0, we got a value of 4. And when x was equal to 2, we got a value of 0. All right. And then finally, we look at our third line, L3, and our critical point was 0, x equals 0, and we got a value of, a y value of 0 at the critical point. Let's see, let me put here, sorry. Critical point, 0, 0, sorry. And then at the endpoints, we had endpoints -2 and +2. They both gave us the same value of 4. All right. Okay. So let's see. Where do we have the largest value here? Well, we just compare all these and notice that our biggest value is 4, and that actually occurs at a couple of different points. So so we can conclude here, the absolute maximum value of this function is certainly equal to 4 on this particular triangular set. And this occurs at, let's see, the 2 points we got here was on L2, let's see, on L1 and L2, that was actually when x was equal to 0, when x was equal to 0, and we're going to find if that's the same thing as for L3, when we got the 2 points for L3. So this, for here, this is going to be then 0, 2, 0, minus 2, and that's the same thing here. Those are the same 2 points for L3 at the 2 endpoints. So for those 2 places, we have our maximum value at those 2 points, and then our minimum value here was way back when we got the critical point of the function. We found the critical point was inside our set, and when we plugged it in, we got a value of -1. So our absolute minimum value is equal to -1, and that occurred at 1, 0 inside of our set. Yeah.
I'm not really understanding, like, what are these guys, because they only go up to 2, so how do they have a 4?
Okay. Now, the values that we're looking at are the values of the function. Okay, the values of the function, where that is biggest and smallest. You're correct as far as actually looking at our triangle. Our triangle, we go to 2 here for the x, 2 here for the y, -2 here for the y. That's our input values.
So do you mean this is like in the z direction?
Absolutely, right. Absolutely, right. This is a function of x and y. So basically, I should have done this on Maple and shown the graph. So yes, it is. It's something here. Let's go here. Now this thing is actually this is x, y, and z. Our little triangle here is, what does it do? Let's see. It goes a little bit in both directions on the y, in the negative direction. So here in the xy plane, this is actually the triangle of input values, okay? Because we have y equals -2, y equals +2, x equals +2. And then we look here, you're right, we then have this flying carpet above it in the z direction when we plug it into our function.
And it's the same shape as the triangle?
Yeah.
Or we just
Yes, as far as if we projected that shape flat down onto the xy axis, it would fit on the triangle. Right.
Okay, so that might actually be more room, but we're just looking at those points that are bounded by the triangle.
Yes, we are. We are just limiting ourselves. For whatever reason, all we care about is what's happening on that triangle. Okay. All right. Good question.
So the absolute max, how come we had 3 of them that equaled 4 and only 2?
Well, let's see. We had 3 of them that equal 4. Yeah, and they turned out to both be the same. Yeah, they turned out actually to be the same points. Where's my drawing here? Here on L1, let's see, on L1, when we looked at L1, it was this point right here that gave us a value of 4. But when we look at L3, yes, of course, this again gave us a value 4, and then This gives us a value for, and this one had already counted for the L2, so we kind of have, you're looking at the same points twice in a way, all right? Yeah. All right. Okay. And I'm only going to do one example of that. You have one of these in the homework, and I was hoping that I made it something that wasn't too horrific. All right. Takes a little bit of time.
That was like 30 minutes.
Yeah, I know, but that's all the explanation. I know you guys are just going to be whizzing through that with lightning speed. All right, let's get this stuff together here. All right. All right. So now we're at the last section that's on chapter 14. And this chapter is titled Lagrange Multipliers. After a French mathematician. Okay. Now, in the previous section, we were looking at finding. We had a function of two variables, and we were looking. Well, where do we have the top? Where do we have the top of the hill? Where do we have the bottom of the valley? All right. A local maximum and local minimum. Here, we again have a function either of 2 or 3 variables this time, 2 or 3. But say with whatever design we're working with, this is like real life situation here, our variables have to have a certain relationship to each other. Our input variables have to have a certain relationship. And that's called a constraint. And what we're trying to find here is, given that constraint on how the variables have to be related to each other, we're trying to find the biggest or the smallest value of the function. Okay. So let me put this down. Here, we're trying to find the biggest or smallest value of, now it could be either a function of 3 variables, in this case it's a function of x, y, and z, or it could just be a function of 2 variables with the constraint. And here with 3 variables, this function here of x, y, and z equaling some constant, that gives us the relationship that for whatever reason we have to have between the 3 variables. And you'll see this more concretely when we do examples. And of course, if it's 2 variables, it would be g of x, y equal to some constant. Okay. All right. Let me show here a bunch of level curves. Here we're looking at a function of 2 variables, f(x), y, and this is the constraint that the variables x and y have to meet. It's some function of x and y equal to k. So this, we can plot this on the x and y axis. That's our constraint. Now what we're wanting to do is find, say we're wanting to maximize our function. Now here's the function that we're wanting to maximize, in this case function of 2 variables, f(x), y. And what this is showing are various level curves. So fxy equal to 11, fxy equal to 10, 9, 8, 7. All right, they're contour curves. And we want that value of fxy to be the biggest value it can be. So looking at this, if fxy is equal to 7, okay, granted, it does meet our constraints, because we also have to have the constraints satisfied, but notice we can get even bigger values of fxy. We can push it, we can look at, say, 8. We still have 2 points that meet our constraints, but yet we can go even bigger. We can go fxy equal to 9. It still meets our constraint, but we can still go bigger. In this case, we can go to fxy equal to 10 and give us a maximum value of 10 where it just touches that constraint curve at a single point as a tangent line. So these two, here's our constraint, here's the function we want to maximize, and they just graze each other. And it's at that point where they just graze each other that we're going to find our biggest or smallest value. Yes?
How would you know that was like without graphing it?
Okay, that's what we're going to show, how to find this without graphing it. Okay. So the question was, how can we find this without going through all of these contour curves and all this kind of stuff? And we're going to show how we can do that. All right. Now, let's look at, now these two curves, now right there where we have that biggest value, that's where that level curve brushes that contour curve. So therefore, if we drew a tangent line at that point, they would both share the same tangent line. All right? Because they just touch each other, they have a common tangent line. Okay, so this is a common tangent line. All right. Now, what that means then, let's look at if they have this, so we have this tangent line. If we look at a vector that is perpendicular to this tangent line, they're going to be, okay, say we have a vector here that's perpendicular from the one curve, and we have a vector here from the other curve that's also perpendicular to the tangent line. One thing that we saw previously, and let me remind you of this, if we have a level curve, fxy equaling some constant, right? The gradient vector at a point, xy, will give us a perpendicular vector to the curve. The gradient of f, which is the vector fx, comma, fy, is perpendicular to the tangent line of the curve. It's a perpendicular vector, yes. All right. Okay. So therefore, the gradient of so in this case, we have these two touching each other. So let's look here. The gradient of my f function is perpendicular to the tangent line. The gradient of my g function is also perpendicular to the tangent line. So since they're both perpendicular to the same line, they're going to be parallel to each other. Therefore, the gradient of the s function and the gradient of the g function are parallel to each other. All right. Now, remember when we started talking about vectors? Two vectors are parallel to each other if their components are multiples, if the vectors are multiples of each other. So this means, they are multiples of each other. All right. Okay. So basically, this means, okay, that this vector, delta f, this is a vector, is equal to some number, and we're going to call this denote this number by lambda. So this is a number, Greek symbol lambda, some number times the gradient of the g function. For some number lambda. Okay. All right. Now, let's just hold this thought here, because this is going to be the heart of this process that we're going to see in just a few minutes after break. All right. Just the other thing I want to say before we break is this. Okay, what we were looking at here was a function of two variables. All right. The same thing can apply if we have a function of three variables. Let me put it this way, the same argument applies to a function of three variables. Okay. So basically, for three variables, so we have f of x, y, and z. That's our function. And we have a constraint which involves x, y, and z, g of x, y, and z equaling some number k. So what we have then is the same deal. Delta f, again, that's a vector, is going to equal some number lambda times the gradient of the constraint. Okay? Again, that's going to be a number, and that's a gradient of the constraint. All right. Okay. So why don't we take a 5-minute break then, and then we're going to see how we can do all this with algebra instead of graphics.
Yes, sir. Hey, this is a really great question.
Yes.
So on the homework due today, in this section, can you theoretically just substitute in the x and y function?
I don't want you to do that.
Oh, right.
Yes, you could.
Okay.
But I just don't want you to do that.
That seems to be the obvious solution.
Right. Yeah.
Just to confirm, confirm, what was the method that you alluded to here, the method shown in class?
Oh, that was, if you look at the book, those nifty little tree diagrams.
Oh, right, that.
Yeah, so kind of helpful ways just to keep track that you're doing all the components of the chain rule.
Okay.
Yeah.
Okay, so when it says X and Y here, that means the function of X, right?
Yeah, Z is a function of
right.
X and Y.
Right.
In turn, X is a function of ST, Y is a function of ST. So to get all the partials for Z with respect to X, we have to go through all the branches that lead from Z to S.
Right,
yeah.
Oh, so where do we actually write the partials on the tree diagram? Where it says
like along the limb.
Okay, along the limb.
Z, X, delta Z, delta X,
Gotcha.
Z, Y. Yeah.
So we write the actual partials where it indicates the partial, not where it indicates the variable. Okay.
Yeah.
All right, thank you.
Every time it snows, one of the managers calls me and tries to get me to cover the shift. Well, they call me a shift. There's no information. What they call it is head manager, there's assistant. No, I drew it. During the sports season, Enter. Okay, I'm just putting back on here again stuff, that whole bunch of stuff that I had typed at the very beginning. Yeah. Do I know what's that again now? I'll be teaching next semester. You mean the fall semester? Oh, well, hopefully I'll be back to Calc 2. Calc 2, yeah, and algebra, neither one of which you'll need, right, yeah. In the summer, I'm hoping to, at least I'm on the books now to teach elementary linear algebra at UMSL, for anybody who's interested. Looking at Tom, no, he can't do it. Have you had elementary linear algebra yet? Okay, but you can't, all right. Huh? Far away. Oh, too far away. Okay. Anyway, I should start advertising that for you interested folks. All right, let's get started here now. Let's see. There is something here that oops, because I was running late today, I should have this available, but I'll see if I can get it available in just a minute. All right, let's now start looking at the process here of applying this fact that we have a function and then we have another function which is a constraint equation that constrains the variables, and we want to try to find either the biggest or the smallest value. All right. So this is the process here. This is the method of Lagrange multipliers. Okay. And I think I'm going to basically kind of do two columns here, so because they're so similar. The first column is going to be for 3 variable functions. And the second for 2 variable functions. All right. Now, so for 3 variable, what we're finding is finding the max or min values of a given function of 3 variables, f, x, y, z, with a constraint. And I'm calling the constraint function g. G of x, y, and z equal to a constant. And then for the, all right. And then for 2 variables, it's max, min, values of f of x and y with the constraint. Again, I'm calling it the g function, g of x, y equaling some constant. Okay. Now, the first process is this, and this is the hard part, all right? Find all values, for the 3 variables, find all values of x, y, z, and lambda such that the gradient of our f function equals lambda times the gradient of the g function. And we have to always satisfy our constraint, g of x, y, and z equals k. Now let's break this down. The gradient, we know that the gradient of a function of 3 variables is fx, fy, and fz. 3-component vector, right? That's the gradient. And of course, we know the gradient of our g function is going to be gx, gy, and gz. So what we're talking about here is this system of equations. We want the gradient of the f equal lambda times the gradient of the y, of the g rather. So this is what we have, this system. We equate the components. So we have fx has to equal lambda times gx. Fy has to equal lambda times gy. Fz has to equal lambda times gz. And g of x, y, and z has to still equal our k. We have 1, 2, 3, 4 equations here. 1, 2, 3, 4 variables. X, y, z, and lambda. 4 variables. Now one thing is, we don't necessarily have to solve for the lambda. What we're interested in, we definitely want to solve to get the x, y, and z values that solve. All right? Okay. Now we have a similar deal with the function of 2 variables, except at least we have a fewer equations. For the 2 variable, let me just skip some things here. We have our gradient of f now is just fx and fy, 2 components. Our gradient of g is gx and gy. So this is the system that we have to solve. The number 1 equation is fx equaling lambda times gx. Number 2 is fy equals lambda times gy. And then the 3rd equation is our constraint. G of xy has to equal k. That has to be satisfied also. So with this one, we have 3 variables, x, y, and lambda, 3 variables. We have 3 equations. And we don't necessarily have to get the lambda value, but we want to get the x and y value. Definitely want the x and y values that solve. Okay. Now, that is the hard part, trust me. Once we get the x, y, and z values, or the x, y values that solve, then the second part is easy. We just plug those into our f function that we want to find the biggest and smallest value, and we see which is the largest value and which is the smallest value. So the second part is easy. Plug in, so this is for 3 variables. Plug in the x, y, and z values into f of x, y, and z. The largest value is the max value. The largest value equals the max value. And the smallest value equals the minimum value. And we do the same thing for 2 variables, except we just plug in x and y into f of x, y, all right, for 2 variables. All right. So I've got several examples, as I'm going through all these pages, several examples of this. And I'm going to start easy and get a little bit harder, all right? Because I don't want to start harder and get easier, because then I don't want to completely scare you off, all right? So let's start with this problem. So here's a problem. First example. Okay. Find the max and min values of fxy, so it's just a function of two variables, and that function is defined as 4x plus y, with the constraint x squared plus y squared have to add up to 17. Now this right here, x squared plus y squared, that's our g function, g of xy, okay? All right, so what we're going to have here is we have fx has to equal lambda, some lambda, times gx, fx has to equal some lambda, fy, has to equal some lambda times gy, and also our constraint equation has to be satisfied. So here's equation 1, number 2, and number 3. So let's figure out what these are for the first two. Okay, these aren't too bad, I don't think. Fx, y is constant, so fx here is going to be 4, and that's equal to lambda times gx. Well, gx is x squared plus y squared, so gx is equal to 2x. That's the partial of 4x plus y with respect to x. That's where the 4 came from. So this is the fx. This here is the gx, and we have that lambda. So therefore, we have that, and then number 2 equation is fy equals lambda gy. So fy here is going to just be a 1. And that's going to equal lambda. Gy is going to be 2y. All right. And then we have number 3. X squared plus y squared equals 17. All right. So let me write these a little bit nicer. So we have 4 is equal to 2. Let me put it as 2x lambda. 1 is equal to 2y lambda. And 3 is x squared plus y squared equals 17. Okay, there they are. Okay. Now, most of these require, shall I say, a little bit of cleverness, all right? A little bit of a puzzle. And another thing I want to tell you is that, as some of you have already pointed out, there's never just one single way to solve a system of equations, all right? Okay. Let's see here. Anybody, so this is number 1, number 2, number 3. Anybody see look at number 1 and number 2. On the left side of the 1 we have 4, on the left side of the other one we have a 1. There's something we could do to one of those so we could kind of set them equal to each other? Yeah. Look at that. If we multiply both sides of the second one by 4, well, we're going to get an interesting result here. So our first thing, of course, is 4 is equal to 2x lambda. But let's multiply both sides of this one by 4. So then again we have, and the reason for doing 4 is so we have a 4 on that left side. So now 4 times 2, 8y lambda. Okay. So therefore, notice, we have this is equal to 4, this is equal to 4, therefore they have to equal each other, right? If two things are equal to the same thing, they're equal to each other. So therefore, I can say that 2x lambda equals 8y lambda. All right? Okay. Now, let's see what that gives us here. I want to ask this question. Can lambda equal 0? Well, what happens with equation number 1 if we decide that lambda can equal 0? We end up with a strange equality, 4 equals 0. The same thing for number 2 equation. If we say lambda is equal to 0, we're going to have 1 equals 0. All right? So we see here that lambda, it equaling 0 makes no sense. All right? So note, lambda cannot equal 0. And there's a reason why I'm wanting to fuss about this right now. Because we've got this equality that 2x lambda equals 8y lambda. Now, I want to get rid of that lambda that's on both sides of that equation, which means to do that, I would have to divide both sides by lambda. Well, you want to make sure that you're not dividing by something that's 0, all right? So if we know that lambda just flat out can't equal 0, then we can divide both sides of that equation by lambda, all right? So therefore, let me put down here, we have 2x lambda equals 8y lambda. What we want to get is a relationship between x and y, and let's get rid of that lambda. So let's divide both sides by lambda. And what we get then on the left side is 2x equals 8y. Well, we can reduce this a little bit further, can't we? We can divide both sides by 2 just to make life easier for ourselves. So we now have the relationship that x has to equal 4y. All right. We got this relationship by using equation 1 and equation 2. That's what we used. But we also now have a third equation that has to be satisfied. The third equation is our constraint equation. X squared plus y squared must add up to 17. So now if we just substitute, we know that x has to be 4y. So let's plug in 4y for x in that equation number 3, and we're going to be able to solve for y. So let's substitute in number 3. So now number 3 is x squared plus y squared equals 17. So now I'm going to put parentheses 4y squared plus y squared equals 17. That's 16y squared plus y squared is equal to 17. Combined terms, that's 17y squared equals 17. Divide by 17, that's y squared is equal to 1. So that gives us two values for y, plus 1 and minus 1. So y equals 1 or y equals negative 1. Okay. Okay, well now that we know what y is, we have two instances that for y, now we can figure out what x is. Because remember, x is equal to 4 times y. So when y is equal to 1, the corresponding x is 4. When y is equal to negative 1, the corresponding x is negative 4. So these are our values, x and y pairs that we have to have by using all three of these equations. Okay. Now let's remember, okay, what is it that we're asking for? We're going back up here, we're asking for the maximum and the minimum values of this function for x plus y. So we take our pairs of x, y, plug it in, and we'll get a number, and we do it for the second pair, and we'll get a number for the f function. So plug in to fxy equaling 4x plus y. All right, so the first one is x is 4, y is 1, 4 comma 1. And what do we get? 4 times 4 plus 1, and we get 17. 17 seems to be showing up more than one time in this process, doesn't it? And then let's do the second one. Now x is minus 4, y is minus 1. So we have 4 times minus 4 plus negative 1, and we get a negative 17. So we can conclude that our maximum value of this function is 17, given the constraint. So conclusion. The max, because that's the bigger value, bigger. Smaller is negative 17. So maximum value equals 17. Minimum value is negative 17. All right. That's the first example. Okay. So, like I said, a little bit of, and there could be other ways to do this, of course, but that's what seems to be the easiest way to do it, to do this problem. Are we ready for, I think we can do a second one. I know, I'm excited about it. Actually, I find this stuff, this is some of the fun stuff that I find in math, is just the puzzle stuff. All right? Okay, so here's our second example. Example 2. And example 2 is still a function of two variables. So find the max and min values of, now here it's fxy equaling x squared minus y squared with the constraint x squared plus 1/9 y squared have to equal 1. So this constraint over here, this thing on the left side, this is our gxy function. Okay? So again, we're going to set the two parts of the gradients equal to each other. So we're going to have fx equal lambda gx, fy equal lambda gy, and then our constraint. And then the third one is the constraint. 1, 2, and 3. Okay, so number 1, fx here, here's our fx, derivative with respect to x is going to be 2x equals lambda, and then gx derivative with respect to x is also 2x. Then we have our second equation, Fy equals lambda Gy. Fy now, be careful, there's a minus sign here, is minus 2y equals lambda. And now the Gy, we've got a fraction there in front, that's going to be 2/9 y. All right. Okay, excuse me. So this is, let's look at what we've got here. So we have, okay. Does anybody holler right at this point that I get rid of the 2's on each side of this first equation? That's, I mean, why not, right? So we have x equals lambda times x. And we also have a pair of 2's here. Why don't I just get rid of them? So this is minus y equals lambda times 1/9 y. All right. Okay. Now, let's look at these two again. This is similar to the question. So this is exactly the same question that I asked before. Okay, we've got those two equations. Now remember, we've got the constraint that has to be realized is that x squared plus 1/9y squared have to add up to 1. All right? So the question is, on those two equations, what if lambda is equal to 0? X would be 0. What about y? Y would also be 0. So note, if lambda equals 0, that means both x and y from those two equations would both have to be 0. Now, that presents a problem, doesn't it? Because what happens if both x and y are 0? Remember, there's a constraint equation that has to be met. What happens to the constraint equation? It won't work in the constraint equation. So, won't work in the constraint. So therefore, thus, we can know that lambda is not equal to 0. Okay. Okay. Let's see what else we can get here from this. Now, one thing that helps us with solving equations is this. Those two equations up there, if we move all the stuff over to the left side, we can actually factor something out. And that'll help solve equations, right? Remember, if with equations, we get 0 on one side, and if we can factor the other side, we're getting there towards solving them. So let's look at number 1 here. X equals lambda x. Let's move it all over to the left side, so subtract lambda x from both sides, and we have x minus lambda x is equal to 0. And we have x's in both of those terms, so that means x times 1 minus lambda has to equal 0. So when we have this, that means we can set the two factors equal to 0. This tells us that either x is going to equal 0 or 1 minus lambda is equal to 0. One or the other. Or both. We could have both, but one or the other. And of course, this means either x is equal to 0 or, let's add lambda to both sides, or lambda is equal to 1. All right. Now, what can we do now? So we know that we're going to have one of these two cases. X is 0 and or lambda is equal to 1. We're trying to satisfy all three of these equations. Remember, we're also trying to satisfy x squared plus 1/9 y squared equal to 1. The only other equation that has x in it is our constraint equation. Because the third equation just has lambda and y in it. So what do you think we can do? Yeah. So let's say x can, one of our cases here is x can equal 0. So let's go into the only other equation there that has x in it and plug in 0. So let's plug in 0 for x in our constraint, which is x squared plus 1/9 y squared equals 1. Okay, so that gives us 0 plus, that gives us 1/9 y squared is equal to 1. And isn't that nice that we have a nice perfect square number down there? So that means multiply by 9, therefore y squared has to equal 9. And so that gives us two values for y. Y can equal positive 3 or y can equal negative 3. So let me draw this conclusion here. This is so far what we've got. We know that lambda can't equal 0, and we found that if x is equal to 0, then y is equal to 3 or negative 3. All right. However, that's not our only case here. We also have here, we had x equals 0, or we could have lambda equal to 1. So let's see what happens if lambda equals 1. Now let's look at lambda equaling 1. Our equations are this: x equals lambda x minus y equals lambda times 1/9 y, x squared plus 1/9 y squared equals 1. All right. And now our second case is we're saying lambda is equal to 1. Well, the first equation, that presents no problem whatsoever, does it? That gives us x equal to x. That's good, isn't it? What else happens, though?
You want to equal to 1/9 y.
Yeah. That second equation, if we set lambda equal to 1, what do we get? We get that negative y is equal to 1/9 y. Now, what's the only number that's going to work there? If negative 1 times a number equals 1/9 of a number, yeah, the only thing that's going to work is 0. We all agree on that? So that means y is equal to 0. Okay, if y is equal to 0, what are the corresponding x values? Well, which one do I have to look at here, 1, 2, or 3, to figure that out? Look at number 3. So from number 3, y is equal to 0, I'm going to have x squared plus 0 equals 1. So x squared is equal to 1. That means my two solutions are -1 and +1. So let me summarize here what happens here when lambda is equal to 1. We're going to have y equal to 0, x equals either +1 or -1. Okay. So, how many of these pairs of x and y have we run across? And that's it. That's the end of the road. All right, we've looked at all the possible cases. So what are all the possible xy's here that we've, and it's all summarized right here, that we've run across? Well, here, when x is 0, we have two values for y. So we have 0, 3, 0, negative 3. Now here, we had y is 0 and two values for x. So 1, 0, minus 1, and 0. These are our 4 points to plug in. And that's the original, our f function. And basically then we see which is the biggest and which gives us the smallest, okay? This is the hard work. All right, so let's see, okay, here's the f function. Let me write this down again. fxy is equal to x squared minus y squared. All right. So let's see. I think either one of these are going to give us, this is x, this is y. So that's, either one of those are going to give us negative 9, right? Minus y squared, negative 9, because the x is 0. And these two, y is 0, x is plus or minus 1, those are going to give us a value of 1. So we can conclude that 1, which is the bigger number, 1 is the absolute max value, subject to the constraint, and negative 9 is the absolute min value, subject to the constraint. Okay. I don't think the next example can be done in 5 minutes. So we'll just hold it there, all right? We've got some more examples to do with this. So I'm just going to keep doing this for the rest of the semester. We're just going to keep doing these problems. Just kidding. All right, so we'll see. Keep your eye on the sky and keep tuned to KSDK or wherever you get your weather information from to see whether or not we have class on Monday.